Hi everyone. So today we're going to talk about integration of complex functions. But first I want to just remind you how things work for functions of real variables back from Calc 1. And we'll kind of use that intuition to define complex integrals. So what is the integral of a function f of x, where x is real, from an interval a to b? So the idea, remember, we've all seen this picture many times, is coming from area under the curve. It's one way of thinking about it. And one way of approximating this area is we break the curve, well, we break the base interval into a bunch of pieces, right? So I'll call A x1, here's x2, x3, x4, etc., xn. Sometimes these are broken up into evenly spaced pieces, but you don't really necessarily have to do that. So we could look at the length of each of these subintervals, call them delta 1, delta 2, delta 3, etc., if they're different lengths. And the approximation for the area under the curve is just given by the area of these rectangles, where the height at some xi is f of xi, and the width is delta I. And so we can approximate this as a sum as I goes from 1 to n of the area of the rectangles, which is height times width. So the height is f of xi times width is the length of the subinterval. And for this actually to be an equality and just not just an approximate equality, we have to take the limit as the number of these subintervals goes to infinity, and kind of making sure that each of the lengths of the subintervals gets smaller and smaller and smaller. Anyway, if you do this precisely, you can define the integral as a limit of a sum. And so we want to kind of repeat this idea for complex integration. Okay, so now we have a function which is complex. Maybe it's not defined on all of C. Maybe it's defined on some subset G, but let's not worry about that right now. So I'm just going to draw a picture of the domain and where it lands, which is another copy of C. Of course, I can't draw the graph anymore because that would be four-dimensional, but here's our picture. And what we're going to do is we're going to integrate the function f over some path. Maybe our path looks like this. And I'm going to specify a direction to the path. And so here's our starting point. Call it z1. And our ending point, call it maybe Cn, something like that. And I want to define what it means to integrate the function f of z over this path. Let's give the path a name. Call it p. Okay. So we're gonna just work by analogy with this Riemann sum here. So we're gonna break our path into pieces. And so I've got a z2, z3, zi. And I'm going to look at a sum, summing over each piece. So I goes from 1 to n. And I can't really think of these as rectangles anymore, but I can still multiply. But what am I going to multiply in here? So instead of the height of a rectangle, I'm going to just multiply f of zi instead of f of xi. But then what do I put here? Well, what I want to look at is each of these subintervals, but I want to think of them not just in terms of their length, but as actual complex numbers. So if I draw a line between each of these points I've marked, I get a vector, v1, here's a v2, v3, etc. And I'm thinking of these vectors as complex numbers. So in particular, v1 as a complex number, I could write this as z1 minus z2, right? That's what complex addition tells us this vector is equal to. z2 minus z1 I meant to say. And similarly, the general vi is equal to, I guess, zi plus 1, so the next term minus the initial term. Zi plus 1 minus zi. And that's kind of what's taking the place of just these subintervals here, the length of them. Now we have a length and a direction, so I want to think of them as actual vectors, which in complex analysis you can represent as a complex number. So I'm going to multiply using complex multiplication f of zi, which is kind of like the height of the rectangle, times something like the width of the rectangle, which is just going to be this complex number vi. And I'm doing that for each of these subpieces. And then I take the limit as n goes to infinity, and that's, if you do this precisely, you get a well-defined answer, and that's what we're going to call the integral of the function f of z along a path p. And notice that this is why the direction of the path is important, because these vectors v1, v2, v3, they have a direction to them, and that's, if you switch the direction of the path, you're going to get the negative of what you would have had. Okay, so the next question is, how do we actually calculate this thing? Because as you know from regular calculus, calculating an integral as a limit is usually not the easiest way to go. And this is where parameterizing paths comes in. So to calculate, we need to parameterize our path p. So let me draw a picture of the domain of our function again. Here is our path p. And remember from chapter 1, a parameterization is a function from an interval into the complex numbers whose image is this path. So let's let gamma be that function, depending on the input real number t, and it goes from some interval a to b to c. And so we're starting, this is gamma of a, here's gamma of b, and so I can represent this function gamma from the interval to the complex numbers as a function like this. Okay, and so now one way to break up the path p is just to break up the interval in the domain of gamma. So I could let this be t1, t2, t3, etc. And so then gamma of a is gamma of t1. That's my z1. My z2 is just gamma of t2. z3 is gamma of t3, etc. Okay. Now, the hardest part of this definition, the thing that's the most new, is these complex vectors vi. So the question is, how do we express those in terms of gamma? And the way we do this is we use the derivative of gamma, because if I consider, so maybe this is zi, which is gamma of ti. If I consider gamma prime at ti, that gives me a vector. And if I attach it to zi, it's going to be tangent to the curve. And so if I do that at each of the ti's, I get a bunch of vectors tangent to the curve. And so if I scale them appropriately, they kind of give a nice approximation of these segments of the path, exactly because they're pointing in the right direction. So let me write out what I said. So I can approximate the vector vi, which is supposed to itself be kind of approximating part of this path, by looking at gamma prime of ti, and I have to scale it appropriately. Basically, it depends on how fast I'm going. And if you think about it, the correct thing to scale it by is just the length of the corresponding interval. So here's delta ti. And if I scale it by this length, then that's going to give me a vector that nicely approximates that piece of the curve. Just to remind you, what do I mean by, so gamma is a function from the interval into c, so what do I mean by its derivative? I just mean, gamma has its real and imaginary parts, and I mean the derivative of both of them with respect to t. So if gamma of t is u of t plus I v of t, then gamma prime is just u prime of t, derivative with respect to t, plus I v prime of t. Okay, so this is something we can do, and then let's look back at this expression here. Now I can write that in a way that's a little more useful. So the integral of f of z dz is going to be the limit. And what's nice now is I can kind of do everything over the interval from a to b. So instead of breaking up my parameterized curve p, well, the way I do that is by breaking up the interval from a to b, right? So going from 1 to n. Now previously I had f of zi, but in terms of gamma, zi is just gamma of ti. So this is just gamma of ti. And then vi, we just said, well, that's just gamma prime of ti times the length of the ith interval, delta I maybe, delta ti, I don't know. So if all the intervals were the same length, that would just be delta t. So I don't know, maybe we assume they are all the same length. Then that's a delta t. We take the limit as n goes to infinity. And this now is something we can make sense of just using our knowledge of real calculus. So this is just some function of t, and we're integrating it with respect to t. And so this becomes equal to, in the t variable, the integral from a to b of f of gamma of t times gamma prime of t with respect to t. Now you might still be a little concerned about this integrand. How do we integrate this with respect to t? Because these are complex numbers. but that's okay. We just use multivariate calculus. So this is, it's a function that lands in C, so it has its real and imaginary part. Maybe I shouldn't use U, I already used U. So it's got the real part x and the imaginary part y. So if I label the integrand as x of t plus iy of t, I break it into its real and imaginary part, then this integral is just first integrating the real part and then integrating the imaginary part. And now we've really broken things into just the usual integrals of single variable functions with real variables. So this is something you know how to do. Okay, and so the main new thing here is parameterizing the curve, and then from there on out, everything should be pretty familiar to you. So let's do an example. Let's say f of z is 1 over z squared. So this function is not defined everywhere. It's not defined at the origin. So if I'm going to have a well-defined integral, I better choose a path that doesn't go through the origin. So I'm going to choose a path on the unit circle from 1 to -1, going counterclockwise. So we want to calculate the integral over this path of the complex function 1 over z squared. Okay. So the first step is to get some control over this path, which means we need to find a parameterization. So I choose a function gamma of t from some interval to c. And so I need gamma to, I need its image to be this semicircle, and I need it to start at 1 and go to -1. So I want gamma to go counterclockwise on the unit circle from 1 to -1. The easiest way of parameterizing the unit circle, or part of it, is to use e to the it, because these points are always on the unit circle. And remember what this means. This is just cosine t plus I sine t. And the way I've written it, this is already going counterclockwise. If you wanted a clockwise path, you would just put a -t in there so that it goes the other direction. But counterclockwise is what we want. And we want it to go from 1 to -1, so we can let our t go from t equals 0 to t equal pi, and that'll do the job. All right. And so we've got our parameterization. By the way, it has to be, one thing I didn't mention is it has to be smooth. And if you remember from the book, a smooth parameterization just means the derivative exists. And you see from our formula exactly why we need the derivative of the parameterization to exist, because it comes into the integrand that we're calculating. And so that's step 2 is to calculate gamma prime of t. And so I'm taking the derivative of e to the it, and it is just, so as you now know, the derivative of the exponential function, the complex exponential function, is the same as the usual derivative. It's itself, and using the chain rule, because we've got a it inside there, this is just going to be I e to the it. Okay. So once we've got the derivative, we can write what the integrand is that we're going to calculate. So the integrand is always f of gamma of t times gamma prime of t. And we're going to be integrating this over t, which remember meant looking at the real and imaginary parts separately. So we need to write this in terms of its real and imaginary parts. Okay. So f of z is 1 over z squared. And so f of gamma of t is going to be 1 over gamma of t squared times gamma prime of t. So this is equal to, gamma of t is e to the it, so 1 over e to the it times gamma prime was I e to the it. So let's see. I should have had the squared here. So one of the denominators cancels with this e to the it, and this is then equal to just I over e to the it, which is I e to the minus it. I need to write it in terms of real and imaginary parts. Well, remember e to the iy is cosine y plus I sine y, and so this is equal to, pull out, I've got the factor of I out front, and it's cosine of minus t is what's being multiplied by I in the exponent, plus I sine of minus t. And if I multiply the I back through, this becomes negative sine minus t plus I cosine minus t. And then step 4 is integrate what you got above. And remember, we're integrating the real and imaginary parts separately. So we're integrating now from 0 to pi, f of gamma of t, gamma prime of t, dt, which we calculated is negative sine of minus t plus I cosine minus t dt. We break this into its real and imaginary parts. And then we integrate. So the antiderivative, with complex analysis, we can't yet talk about antiderivatives, but this is just an integral of real variables. So I can use the fundamental theorem. Antiderivative of sine is minus cosine. There's a minus there, so we got to get our minuses right. So it's going to be cosine of minus t. So if I take the derivative of this, I'd get a negative sign with another negative, so it'd be positive. So I need to add a minus there for the correct antiderivative. So I evaluate that from 0 to pi, and then plus I times, looks like it'll be negative sine of minus t, again from 0 to pi. Okay, and now we evaluate. It just so happens that sine of 0 is 0, and sine of pi is also 0. So this part is 0. And let's see, so cosine of negative pi is, I think, minus 1. Taking the minus of that, so I get 1. And cosine of 0 is 1, so the negative of that is minus 1. And so I'm getting 2 as my integral, if I didn't make any mistakes. Cool. So that's the number that we get. A few things to note is it depends on our path. I mean, obviously, if I did a completely different path, I'd get a different answer. You might wonder, what if I did a path that started and ended at the same point? Well, you can get a different answer there as well. So it does depend on that path. But another thing is, does it depend on how I parameterize my specific path? Like, what if I had chosen gamma 2 of t to be some other parameterization of this half circle? So an easy way to do it would be like, I don't know, e to the I 2t. So this one's going twice as fast, so it's just going to go from t equals 0 to t equals pi over 2 in this case. That would also give me a parameterization of the half circle. And it turns out these integrals don't depend on the parameterization, which is something you can check using chain rule. So the fact is that the integral over some path, does not depend on how I integrate. That's not what I meant to say. It does not depend on how I parameterize the path P. But does depend on choice of path. Okay, and then one other thing I want to mention. So sometimes you might get a path which seems a little tricky to parameterize in a smooth way. So for instance, maybe my path is a square. So I don't know of a good succinct way of writing a parameterization for a square, except by kind of doing the 4 pieces individually, and that's fine to do that when you're looking at integrals. So if this is P1, P2, P3, P4, and the whole thing is P, then if I want to integrate over the entire square, some function, I can do this by integrating over each piece individually. So I integrate first over P1, then P2. So I integrate over all the PI's, my function. And that'll give me the correct answer. And so if you see something that it's easy to parameterize the pieces, but it's hard to parameterize the whole thing, just do it piece by piece, and that's the easiest way.